thank you for your grace and goodness to us. Thank you that you love us so well. And I ask your blessing. Well, I ask your blessing on this class, certainly. But Father, from what I understand, the weather that's going to happen in Kentucky over Louisville way and not so much right here exactly, but Lord, it's going to be real hard for a lot of people. And I pray you just extend grace there. I don't know what you want to do for any given person or family, but you know who they are and what the needs are, and you can respond to those needs, that people will be able to see you in the midst of a storm. And I pray you do that, Father. You do something to extend your grace right there. And help us, Lord, to do what we can do. Interceding for them, I don't know what you'd have us do, but whatever it is, would you give us grace to do that. Thank you, Father, in Jesus' name. Amen. Okay, so this is on the first page and a half of this galactic radiation thing. There's one inside the sun, we've covered that. So the next one is solar activity. Back of the second page, and that's what we're gonna cover right now.
I don't have the last paragraph on the sun page because it was like the end of class and I didn't get to write it down.
Okay, we'll do that later.
Okay.
So, solar activity, there we go. So we're talking about I mean, we made mention of the sun last time. Basically, the sun is big and bad right in our own solar system. It's the one star that's there. And so you can get a copy from someone else. I will try to redo this thing so you have at least these first couple of pages. But Wien's law, we talked about that. The longer the wavelength, the lower the temperature. That's this little, under the sun, this little formula. You need to know what that formula is doing, or how it works, what it will output. So, solar activity is shaped by magnetic fields and driven by the powerful flow of energy rising from the sun's interior. So, and we don't know exactly what's going on in the sun's interior. I have a whole, not a class, a couple of pages that I'm not gonna bother with this semester because I don't think it's pertinent. And so far it's speculation. There are different ideas about what is generating this thing in the sun. What's internally generating. They don't know. There's speculation. In fact, I watched something the other day. We covered it, well, Jason, Leslie said about that he's recorded what they were gonna see. Well, I saw something else the other day, a secular view that said they had to redo what they think about the Big Bang because it didn't reveal what it should have revealed when they looked back as far as they did with the James Webb Space Telescope. So, it wasn't just a creationist saying it. Secular science is saying, well, something, it's not what we thought. We hypothesized that this would be, and the hypothesis hasn't worked out the way they thought it would. So, but we don't know what's going on, what's generating this stuff in the sun. There's speculation, but that's what it is, and I'm going to leave it at that. So the solar maximum, every 11 years, there's a maximum, over a course of 11 years, there's a solar maximum and minimum. And the maximum is when there are a lot of sunspots. And where there are a lot of sunspots, there's more sun activity. And when there's no sunspots or fewer, there is a lot less. So solar maximum talks about solar activity, and the last maximum was April 2014. And so they're anticipating the next maximum. Now, they're not sure, but the next maximum should be somewhere in the summer, early summer of 2025. This is, there's a solar max in April of 2014, and there's the minimum in 19, and you can see here on this that it looks like a lot's happening here, and it looks like it's pretty sleepy over here, and that's kind of what it is. This isn't showing you sunspots, it's showing you activity here. There's more activity, more.
Is there nothing?
Yo,
Not the Zoom. The Zoom class.
It's on.
it's on.
Just the screen's on.
Oh,
The L's on.
yeah. Thank you. So the solar minimum in this last cycle, before this, the one we're in, between these two cycles, 24 and 25, we're in 25 now. So it was it's the sunspot number fell to 1.8. This means that we've been in the solar cycle 25 since December of 2019. So that's how they measure it, where that level. So you've got the maximum and minimum. The weakest solar, the solar cycle before this one was the weakest in history since they've been keeping books on it, or the fourth weakest. Solar cycle 1 in 1755 was the first one that they started keeping, and that one, let me talk about that one for a minute. Sunspots, those are sunspots.
Mr. Johnson,
Yo,
at the risk of sounding foolish or forcing you to get ahead of yourself, which if you're going to,
Yes.
just let me know.
I'm gonna get ahead of myself, I'm sure.
Other than just general heat, is there any way that we on Earth experience this?
Experience,
The solar maximums that we're talking about?
oh yeah, oh yeah.
Okay.
During the solar maximum and the minimum both, there was a minimum, let me see. Yeah, let me do this. So this is in 2000. So this is, you see little sunspots. Now these little sunspots, well, I'll show you in a minute, the size of the Earth compared to these sunspots. They look pretty negligible. I mean, listen, nothing. And this one, oh, they're not there. That's a solar minimum. And this would be, I don't know if this is a maximum, but it shows the contrast. And then this illustrates, so those little teeny dots you saw, and this is the relative size of the Earth compared to them. So these things are big. And out of this solar activity, when you got a lot of solar activity, a lot of sunspots, you got a lot of transformational stuff that's happening on the sun. And these, having a lot of these can result in coronal mass ejections, where they shoot out plasma into space. And the issue is, if they're shooting plasma out our way, I mean, if the Earth is here and they're shooting it out over here, well, it doesn't do a whole lot. But if the Earth would be right if it's shooting it out, if it happens to, out of that huge sun, shoot it out directed toward the Earth, you can have a lot of stuff happen. This I mentioned before, where there was a lot of activity in 1859, I think. So telegraph operators would get shocked, and the paper they're recording on would burn up. I mean, because the magnetic, and you see northern lights as far south as the Caribbean. They were seeing them, because the electromagnetic energy that's shot out, the plasma that's shot out from the sun, our magnetic field around the Earth will deflect a good portion of it, but it can come in at the north and the south poles. And if you get a lot of it, if one of these coronal mass ejections or a solar flare shoots out toward the Earth, when the Earth is in its way, the solar plasma will tend, will go in at the top and the bottom of the North and South Pole. And that's where you get northern lights at the northern pole. But if a lot of it goes in, it'll cause electrical reactions all farther south. So yeah, it can. And when there's nothing happening, and if nothing's happening for a long period of time, you can get, like in 17, let me see. Let me go down to this. I'm getting it to it. So, the most prominent example of solar activity, sunspot seems to be dark because it's cooler than the rest of the photosphere. So you wrote that in your papers, you've already covered that. But the reason why it looks dark is because it's cooler, but it doesn't mean it's cold. The average sunspot is about twice the size of the Earth and more, and contains magnetic fields about 1,000 times stronger than the sun's average field. Sunspots are thought to form because the magnetic field inhibits rising currents of hot gas and allows the surface to cool. So, when they say are thought to, means they're not sure. That's not a bad thing, but it just means that it's not conclusive. They think that that's what. The average number of sunspots varies over a period of about 11 years. That's a sunspot cycle is an 11-year cycle. It's related to the magnetic cycle, but the sunspot cycle does not repeat exactly each cycle. The decades 1645 to 1715, known as the Maunder Minimum, the Little Ice Age, where temperatures were lower around the globe, seem to have been at a time when solar activity was very low. So, Little Ice Age. Places had ice that usually didn't get it. Early records of sunspots indicate the sun went through a period of inactivity in the late 17th century. Very few sunspots were seen on the sun from about 1645 to 1715. Now that's a long time. 70 years. So 70 years is several sunspot cycles, but you didn't get many. And so the temperatures, if you Google Maunder Minimum and read about how that affected the planet, it really did affect the planet. And that was the lack of sunspots. When you have a lot of sunspots, you have more opportunity for the sun to shoot them at the Earth. It shoots them, it'll shoot them out, but it's got to be directly focused on our planet to cause trouble. In fact, I think in one of the questions in 1989, there was a power grid outage in Canada that kept people in the dark for, I guess 9 hours. The power grid went out. It just overloaded it and took it out. So, although the observations were not as extensive as they are now, the sun was in fact well observed during this time, and lack of sunspots is well documented. The period of solar activity also corresponded to a climatic period called the Little Ice Age. Imagine that, Little Ice Age, when rivers that are normally ice-free froze and snowfields remained year-round at lower altitudes. So it really was. It really disrupted a lot of stuff. This doesn't have anything, I don't think this has anything to do with sunspots. I haven't checked it out. But in the 30s, late 20s and early 30s, people used to skate out here on the North Fork in the winter. You get your ice skates and go zooming. Now, I don't know if it happened every year. I've got photographs of people back in the day that were workers here skating on the North Fork. Now, they did flood control, which changed the dynamics somewhat, but nonetheless, they could skate on it. It hasn't, I mean, you've seen ice on it, but it wasn't ice. I mean, you can see ice, but not any buildup enough to go out on. So anyway, there's any evidence that the sun had similar periods of inactivity in the more distant past. The connection between solar activity and terrestrial climate is an area of ongoing research, so they don't know. But this is sunspot number here, obviously, and the date. So right in here, there was almost no activity for 70 years. And then you start to get sunspot activity, and here in the late 1800s, it's high. 1850s again, it's getting high. 1950, and then this only goes to 2000. But now it's pretty low. This sunspot cycle 24 has been relatively chill for most of its existence, most of the 11 years or so that it's been being monitored. The chromosphere, occurring in the chromosphere, a prominence occurring in the chromosphere are composed of lots of hot gas trapped in magnetic fields. So magnetic fields are trapping these things and then they blast out of there, extending in arc shapes above the active regions. So here is an this is a photograph of a prominence. And this is a prominence, and having the Earth, the size of our Earth imposed to give you some measure of its size. So the Earth would fit right in here, and this prominence would certainly dominate our Earth. So prominences occur in the chromosphere. Solar prominence, that's in 1999, that's a big one. There are some pretty, if you look at this stuff online, there are some pretty neat things they show some amazing things, I think. Oh, well, let's see.
You have to be able to take care of yourself so you can take care of your loved one.
Hello, this is Dr. C. Alex Young with NASA's Goddard Space Flight Center and the Sun today. It's June 7th, 2011. I woke up this morning to an email from a colleague of mine, helioviewer.org, that said, "Never seen anything like this before, spectacular." And I can't think of any better way to describe this event. This morning at around 7 UT Universal Time, over a period of maybe 3 hours or so, the sun produced a quite spectacular prominence eruption that had a solar flare and high energy particles associated with it, but I've just never seen material released like this before, such huge amount, and then fall back down in quite the spectacular way. You can see a wave coming, there's the flash, and all of this dark, relatively cool material compared to the corona falling back down on the sun. You see it brighten up as it hits the solar surface, and in some places you can even see it appears to get sucked back in because it's magnetic and it's being attracted into the areas of intense magnetic field called sunspots or active regions. And it looks like somebody just kicked a giant clod of dirt up into the air and then fell back down. If you move up to a slightly hotter temperature in the corona, around 700,000 degrees, the material is darker.
So that's what they've done. What they were looking at, they were looking at the sun at a specific light range. And now they've moved that up and they're, yes?
Jacob said he couldn't see the screen.
Well, I will, Jacob, I will put this online for you. Let me see, you're there. I'm sharing the screen, it should be shared. Let's see if this works there. Yep. Okay. So this is taken at a different measurement of nanometers, which was what you use to evaluate the spectrum. So radio waves are certain nanometers, gamma waves are at certain others, and this is a little hotter. This is a little more intense heat, a range that they're looking at the sun, so that's why the difference in color. And they can do this a couple times.
Because it's much cooler, but you can still see the wave and all of this material come falling down. We can move up to even hotter and higher area in the corona. And again, you see this wave as the event lifts off. It's even easier to see here. The material is even darker now because it's much, much cooler than the corona at this point, which is about 2 million degrees. You can see it falling down, heating up as it hits the surface. So this is just really an amazing, amazing event. It's not necessarily anything spectacular as far as space weather, but it's just really, really beautiful. And at the very end of this image, these images from Alaska, we can see the very beginnings of this CME as it leaves the sun. Very bright, complicated structure. So, as you can see, again, it's a very spectacular event. It produced a pretty nice size M2.5 flare and some solar energetic particles or protons. But it's nothing we really have to worry about. But it's just really, really beautiful. So I hope that you enjoyed it. So thank you very much.
So, you not needing to worry about it is a function of it wasn't directed our way. In one part, it wasn't directed directly toward the Earth. If it had been, I don't know how, well, I'll show you. So solar flares, a violent outburst. So this is not a prominence, this is a flare. A violent outburst on the solar surface that grows to a maximum of a few minutes and decays in an hour or less. During that time, it emits vast amount of X-ray, ultraviolet, and visible radiation, plus streams of high energy protons and electrons. So this is shooting that stuff out, solar flare. And we can be affected by solar flares here. The radiation from flares, particularly X-rays and UV rays, reach the Earth in 8 minutes and 20 seconds. They travel at the speed of light. So these things are traveling about the speed of light, like all wavelengths traveling from the sun. You should remember that I don't know, but if I could remember to write this in a test, I would say, do all wavelengths travel the same speed from the sun? Or yes or no, they do, whatever. So, increases the ionization of the Earth's upper atmosphere. That means it messes with the atoms, the atomic structure that's up there. It does things to the electrons predominantly. Flares also eject high energy particles that travel much less than the speed of light. So their effect is like a gust of solar wind, may not be manifest on Earth for hours or days after the flare occurs. So the flare could occur, you'd get some stuff traveling that get there quickly, and other stuff that would take a much longer time to travel that distance. They don't travel the speed of light. They travel really fast. But 186,000 miles a second is really, really fast. So it can still go really fast, but not as fast as that. So this is again, this is a solar flare, size of the Earth in regard to that solar flare, so that's a huge thing. So they could alter reflection of shortwave radio signals and disrupt communications and general surges, high voltage power lines on Earth, as well as produce radiation hazards to passengers in supersonic transports and in spacecraft. So that's one of the reasons why they think it's feasible, I believe they think it's feasible, to spend money on studying the sun, because we are becoming more electronically dependent. And if they can see something happening and have some kind of lead time to shut things down before they get shut down, it will benefit we dwellers on this planet. So this is a diagram. So you've got a solar flare, and you can see if this was a little solar flare, and it would happen to be pointed at the Earth. And this sun is huge compared to the Earth. This sun is really huge, and it's got these solar flares going off. I mean, when it does, it's got sunspots, and it's got the solar flares going off. Well, they can go off in a lot of different directions. It doesn't have anything to do with this, but once in a while, you'll get one that lines up directly with the Earth, and it'll shoot right toward it. And so our magnetic field protects the Earth from the direct act of these solar radiation, and but they can come down. This is where they'd come in. If they were gonna come into the Earth, they would. Now, some probably does cross this stuff, but basically this magnetic field takes care of them, but they come down, they follow the line of least resistance, come in north and south poles. That's what they do. So, and then it also shoots beyond the Earth. In fact, this stuff will continue going out until it goes out, and it's part of making up that helios sheath that protects our solar system from interstellar space, this stuff. So it has a reason. It can be bad for us if it's aimed at us, but it does good generally. So, and this is a similar thing. The numbers don't mean anything. But once again, it can affect planes, electrical transformers, the spacecraft. It can affect all that stuff. But it typically will come in and down at the poles. And they're pretty good. I mean, the ones that they can monitor that aren't, they're pretty good about warning people, like people operating in spacecraft. If they're operating outside and something like that happens, they tell them to get in. Okay, so this is a quick one. So CMEs and flares are not the same thing. And they used to think that they were somehow connected in their activity, but they found that they're not necessarily. So flares are sending out particles at the speed of light, which means they travel 8 minutes and 20 seconds to get from the sun to the Earth. CMEs, coronal mass ejections, however, are shooting plasma, and it takes them a lot longer to get there. So, every so often, this is what somebody wrote, and I kind of liked it. The sun burps with the power of 20 million nuclear bombs. These hiccups are known as coronal mass ejections, CMEs. So CME and a flare, they're not the same. They're powerful eruptions into the sun's surface, driven by kinks in the solar magnetic field. During a CME, enormous bubbles of superheated gas called plasma are ejected from the sun. Over the course of several hours, 1 billion tons of material are lifted off the sun's surface and accelerated to speeds of 1 million miles per hour. That sounds really fast, except traveling at that rate, where we're 93 million miles away from the sun, it's a lot slower than the speed of light. So it takes these things a little bit longer to get there. So they see CMEs, so they cover the sun itself, so they're just seeing what's going on around the edges of it, and that's where they look at the CME. So this is if you look carefully, you'd see some of these things were exploding out and then forming like rings. So that, not rings, but they were flowing out and then back in. So those are some of the magnetic fields. That's what they're talking about, that they're magnetic fields that are being twisted. The sun is gaseous. The sun isn't solid, it's gaseous. So as a result, it's moving, and some of these, they believe that the magnetic fields can get twisted, and as they get twisted, then they can erupt. And CME is coronal mass ejections. So, underlying cause of these things are not well understood. Astronomers agree that the sun's magnetic field plays a major role. They don't know how exactly, but it plays a major role. Because the sun is fluid, turbulence tends to twist the magnetic fields. Complex contortions twist the field too much, it kinks. Much like a foam cord or a toy slinky, these kinks snap the magnetic field and can potentially drive vast amounts of plasma into space. And what we have from a CME is plasma. That's why it's not traveling at the speed of light. It's plasma. It's a cloud of protons and electrons carried aloft by the solar wind. The ejecta can cross the 93 million mile distance in a few days. Like a jet moving that fast would take you from Los Angeles to New York in 18 seconds, minus the takeoff and landing. So it's still pretty fast. Because they're localized in the sun, they can get blown off the sun in all directions. They're, wherever they are in the sun, when you get a coronal mass ejection, it's gonna go out in the direction that it was facing. So most don't come anywhere near the Earth, but very so often, an eruption is aimed right at the Earth. When a plasma cloud hits our planet, a geomagnetic storm follows, which is why you get the northern lights and the southern lights. You get the northern lights in the northern hemisphere, southern lights in the southern hemisphere, and depending on the severity of the geomagnetic storm, you'll see the lights farther down. The shock wave of charged particles compresses the Earth's day side magnetic field, while the night side gets stretched out like a elongated rubber band. So the side that's facing the sun, when it goes off, that's what it's talking about, like an elongated, okay. Terrestrial magnetic field eventually snaps back with the same amount of energy as a bolt of light. So, that's what, it goes out, hits this, goes down the poles, but kind of pushes the magnetic field in. If we weren't dealing with that, they would be more uniform. But when it is, it pushes this in, stretches this out on the other side of it. But that magnetic field, I don't know much about magnetic fields, or next to nothing. But God has created a planet that has the mechanisms it does to support life in the face of a furnace only 93 million miles away. That, I mean, if it was much closer, we'd be toast. If it was farther away, we'd be icebergs. So it's just, it's not just by chance, obviously. So, the onslaught of charged particles, as I was saying, restructures the Earth's magnetic field to some degree, and auroral lights usually are seen near the poles, can drift lower altitudes and become more brilliant. The disturbance of magnetic field also exposes Earth to deadly cosmic rays. The long-lasting danger comes from the storm's effect on technology. And we are more and more technologically dependent. Here we go, that's right. So technology, long-lasting effect, because this activity in induced electric currents has a potential of severely disrupting power grids. So, assume 1989, in Hydro, 6 million people without power for 9 hours. So it's a photograph. But the 1989 storm is nothing compared to the geomagnetic storm of 1859, known as the Carrington effect, after an amateur astronomer, Richard Carrington, who observed the flares that triggered the storm. It was the most powerful geomagnetic storm ever recorded. Auroras were observed as far south as Hawaii and the Caribbean. Witnesses at higher altitudes reported being able to read newspaper by the light of the aurora alone. Really bright, really intense. Telegraph network around the globe catastrophically failed. Telegraph networks, operators received shocks, and telegraph paper caught fire. A repeat of the Carrington effect to today's far more interconnected world would be devastating. If it just happened and nobody knew it was happening. Cascading failures and quickly shut down power to millions of people in a matter of minutes. Communication networks would fail. GPS satellites, upon which the entire air traffic control system relies, would shut down. So it would be devastating. Obviously, we don't want to be surprised by our power about CME, and that's why astronomers are studying the sun. The understanding of solar activity can help us be better prepared. Even with just a few hours warning before an impending CME strike, we could safely shut down and protect essential services. Disruptions that may last only a few hours rather than days, weeks, and months. CMEs are just another reminder of how fragile our pale blue dot is as it races around the sun. Bottom line. Coronal mass ejections, known as CMEs, are powerful eruptions on the sun's surface caused by instabilities in the sun's magnetic field. Okay? They're powerful eruptions on the sun's surface caused by instabilities in the sun's magnetic field. They can launch billions of tons of superheated gas into space, plasma. Most drift harmlessly across the solar system, but occasionally one is aimed at the Earth. When that happens, geomagnetic storms can severely disrupt electrical systems and produce brilliant auroral displays. So, where you have a coronal mass ejection that focuses on the Earth, what happens? Superheated gas hits the Earth, changes, it results in a geomagnetic storm, and it can severely disrupt electrical systems, produce a lot of brilliant auroral displays. So in 2022, SpaceX witnessed the destructive power of the sun when a geomagnetic storm destroyed up to 40 Starlink satellites worth over $50 million shortly after their deployment. So they sent these Starlink satellites up to operate, and there was a geomagnetic storm. The Earth's atmosphere absorbed energy from the storm. So this is kind of how it works. So the plasma shoots sun comes down to the north and south poles. It eats up the atmosphere and expands it, and that results in the atmosphere becoming more dense. So these satellites are designed to operate in a certain density of atmosphere. Well, when the atmosphere gets more dense, it ends up causing drag. In fact, there's a little picture here. So what happens? I don't think you have this, but anyway. What happens is this. So you've got an orbit that normally would go like this with no drag. That's what it's designed for. It's designed for this operating place, this density of material, of an atmosphere. And when it gets more dense, it causes it to drag. And when it's pulled down, then it can't maintain, it doesn't maintain this orbit. And its drag causes these things to start downward and incinerate as they're meeting the friction of lower atmosphere. So they come down into lower atmosphere, they're going at high speed, and friction will burn them up. So, now I'm not supporting this guy, but I like what he says in this particular piece.
Known for creating memories. No one wants to be known for cancer.
Heard anything about the Parker Solar Probe lately? What's up with that? Parker Solar Probe, named for Eugene Parker. He's a solar physicist who, back in the 1950s, proposed the crazy idea that maybe the sun is releasing particles from its surface in the form of what today we would call the solar wind. And these particles would stream out through the solar system and collide with planets, possibly generating Earth's aurora. Well, how are you going to confirm all this? You can use telescopes, but you really kind of want to go there. Well, that's hard and dangerous because, why? The sun is hot. Finally, the engineering came to pass. The design and construction of this remarkable space probe became a reality. The reason why I'm talking about it is the Parker Solar Probe just made its closest approach to the sun. And how close was that? The closest we've ever sent anything to the sun. 5 sun diameters away. And since the sun has such a huge gravitational field, anything that flies that close to the sun, its speed increases from the gravitational attraction of the sun. And as a result, the Parker Solar Probe has reached the highest speed ever for any human-made craft and hit a top speed of 430,000 miles an hour. So how fast is 430,000 miles an hour? That's fast by terrestrial standards, but in the universe, it amounts to 6/100ths of 1% of the speed of light. So get over it. The point of this is not to show off how fast it's moving or how hot it's become. It's to make measurements of the sun to more deeply understand what we call solar weather. The storms on the sun release particles into space that actually have a way of heating the outer atmosphere of the sun, which we call the corona. The corona is what's rendered visible during a total solar eclipse. It's millions of degrees, much hotter than the sun's surface, for reasons that remain a little bit mysterious. However, it's very sparsely populated by gas molecules. How hot would it feel? I don't know. If a particle hits here and then there, you're not bathed in a complete solution of hot gas if you were in the corona. And it's likely that you could just survive it just fine, even though it's millions of degrees. What would be much more damaging to you and devastating is the radiant heat coming from the surface of the sun itself. And the Parker Solar Probe, why doesn't it melt? Because it's shielded by the substance, the element on the periodic table that has the very highest melting point. What could it be? Is it some metal? Is it the highest melting point element on the table by far is carbon. So there's a carbon composite shield there, rather thick, but nonetheless to protect it from the sun. It is there, always oriented in a way to shield the rest of its electronics, to make the measurements of the magnetic field, the particle flux, the whatever might be the heating mechanism for the corona. It's the sun close up and personal. And I guess we can say that's touching the sun, because the corona is part of the sun's full atmospheric structure and size and shape. But when you're told a probe is touching the sun, what are you thinking? You're probably thinking it's going to skim the surface of the sun. It's like, no, that's not. It's going to be 5 solar diameters away from its surface. Little human interest fact, that there's a little memory card that is flying on this mission that has a photo of Eugene Parker, a file containing his original paper he published in 1958, making some radical predictions in what would become the solar wind, as well as the names of 1.1 million people that want a little piece of themselves, their name, to participate in the exploration of the solar system, and in this particular case, to kiss the sun. The sun, the nearest star in space to Earth. The more we understand it, the better able we will be to accommodate the idiosyncrasies of the sun's cycle. It's 11 and 22-year cycle. Some of it remains a bit mysterious to us. We're scared a little bit because explosions on the sun can send a flux of particles that will have the power to knock out much of our orbiting satellites, unless these satellites are electronically hardened, as the expression goes. So we are particularly susceptible in modern times, given how much of our economy and our national security depends on space assets. The more we know about space weather generated by the sun, the better off we will be. And so that's a little bit of what's up with that.